is discrete Fourier transform actually? So it is your same old discrete time Fourier transform only, but two changes have been made. One is the entire discrete Fourier transform was periodic from minus pi to plus pi. It was repeating from minus pi to plus pi. For a change, we will start from 0 and we will go till 2 pi. That is the first change. Second change is entire space from 0 to 2 pi earlier had infinite number of samples, continuous. Okay. Now entire omega has been broken into the total length was 2 pi, right? Have been broken into n pieces where each sample, discrete sample, will now occur at every k equal to 0, k equal to 1, k equal to 2, and so on. And this 2 pi by n is the spacing between the two samples, okay, the delta omega. That is the second thing. The third thing is the discrete time Fourier transform, whatever we studied, that would earlier exist for aperiodic signals, which may extend from anywhere to anywhere, from say minus infinity to infinity. For a change, we will be taking only finite number of values from 0 to n minus 1. Okay, x of n also will be taking n values. Okay, and in the frequency domain, there also will be taking n values. Okay, for this particular thing. So we had derived the expression in the previous class. We did not derive, we just saw how the derivation has been made. Okay, and we concluded at wait a second. Okay, so we had derived this particular thing, and this is the whole derivation, whatever that has been made. So finally, from this particular x of omega, we have arrived at x of k. From x of omega, now we have arrived at x of k. What is the difference, by the way? First thing is we will be taking only n number of samples in the time domain. In the time domain also, we will take n number of samples. Okay. So actually, for discrete time Fourier transform, x of n was supposed to be aperiodic. Aperiodic in the sense what? It can start from any random value from minus side. It can go to any random value on the plus side. It can have infinite number of values. But we will restrict the values only from 0 to n minus 1. Now, what is this n? This is the same n. Okay. These are actually n is the number of samples which we decided to take in the frequency domain represented by k. Okay. Okay. So this k here represents the value of omega which have been sampled, and this n represents the values in the time domain. Okay. Yes. So this is the expression for DFT, and DFT is a reversible thing. Okay. So you can recover. So just as the way we had, what was that? A sampling theorem, right? What did the sampling theorem say? A continuous time signal can be uniquely represented from its discrete time samples, if at all we take some number of samples, right? So and so. Similarly here, if at all this x of k can sufficiently describe the DTFT of x of n, the x of n can also be recovered from this x of k. Okay, and the formula exists. Okay, and the formula exists. Okay. So as you can see, both the DFT and IDFT, both of them are discrete in nature. Here also there is a summation mark, right? Here also there is a summation mark. This was unlike DTFT, where one of the term had an integration while the inverse had the summation. Okay. Okay, got this particular thing? Okay, now I think we are we can continue from here. So what is the consequence, by the way? See, we have made compromises here. We have made some compromises here. What sort of compromise did we make? While taking the samples, as I said, actual DTFT expression had us considering all the values from minus infinity to infinity for x of n. But since we have taken only finite number of samples, what's going to happen is we are making a compromise. From infinite number of samples, we are taking only n minus 1 number of samples. First thing first. So that is one reason why the DTFT cannot give same analysis for us as the DFT cannot give same analysis to us as DTFT. And the second thing is in the frequency domain, as I keep repeating, if at all there was a big peak here, or say there was a valley here, a peak here, right? So the details in between, now you tend to choose finite values. Okay, so there is a loss chance that data is being lost. So what is the solution? Take more number of samples. The solution means taking large number of samples. More the number of samples, anyway, a larger number of samples, be it 100, be it 1000 or 2 crores, still it is finite, right? That means if at all you can crunch the numbers, fine, you can use a digital computer to do so. Okay. So that is DFT. So we are done with this thing, sampling of the DTFT to arrive at DFT. Okay, so here are the formulae. So I had told you yesterday itself, so it's good to have a pen and a paper with you, so that we can try out a numerical, so that you can also involve. Okay, so yeah, here is a numerical, here is a problem. This is a general problem. Okay, this one is a very generalized problem. What is this particular wave, by the way? X of n equal to 1 from 0 to L minus 1, 0 otherwise. Can you guess what this particular thing is? It's a box actually. 0 to L minus 1. Now we will realize that X of n, it's not like earlier from negative side to positive. Now we will say everything will start from 0 and it will go to L minus 1 number of samples. Okay, these are discrete samples. Do not get fooled by the envelope which I had drawn. Okay, amplitude is 1. So it's a rectangular pulse. So we know DTFT of a rectangular pulse is a sync, right? So we have studied in the previous semester, DTFT of a rectangular pulse is a sync pulse. Okay, is a sync pulse, of course, taking into consideration from minus pi to plus pi. Okay, now can we guess how the DFT is going to look like for this particular wave? How the DFT is going to look like for this particular wave? So once again, let me, okay, so input here, what did I tell? The input here is a rectangular thing. Okay, 0 to L minus 1. So 0 to L minus 1, something like this. Oh God, I mean, yes, something like this. Okay, and it's DTFT, sorry. How was the DTFT? So it was a sync pulse, right? So something like this. It was a sort of a sync pulse. Sync in the sense what? These things, the waves, they keep dying and okay, the amplitude repeating from minus pi to pi. That was the value. From minus pi to plus pi. Now, as I told you, when you do DFT, the values from minus pi to 0 now come on the right side. That means we'll have something like this. Okay, now we'll have something like this going from 0 to 2 pi. Now the values will go from 0 to 2 pi. Second thing is, see, every DFT comes with this particular thing, right? They will ask you to find a 10-point DFT, a 20-point DFT, a 1024-point DFT, 128-point DFT, and so and so. So every DFT comes with this n point. How many samples would you like to have in the frequency domain? Okay, more the number of samples you like to have in the frequency domain, that many number of samples only you can also pick in the time domain also. Okay, for this particular thing. Okay, now let us make this guess, by the way. How the DFT is going to look like for this rectangular pulse? The DTFT looks something like this. Now we will have samples here. Now we'll have samples here. From where to where? Not from minus pi to pi, but from 0 to 2 pi. So many samples. Okay. More the value of n. If at all we take n equal to 100, we will have 100 samples. If at all we take n is equal to 300, we will have 300 samples. Okay. 300, we will have 300, and so and so. Okay. Now shall we see the answer of this? Okay. By the way, the formula, what is it? X of n e to the power minus. This is actually the discrete Fourier transform. Let us draw a parallel from this to our DFT. Yes. Here, this here actually was our discrete Fourier transform. Okay, you see this is a discrete Fourier transform. Now, how does the DTFT for this look like? So this here is going to be our discrete Fourier transform. Okay, you can see here it's still having the same envelope. It is still having the same envelope, something like this. But when I take n is equal to 50, that is somewhat okay, fine. When you take n equal to 100, the envelope you can see is better approximated. Okay, so are you getting now the importance of taking large number of samples? More the number of samples, better is the resolution in the frequency domain. You tend to choose more number of samples in between. Okay, what is the consequence of going for higher value of n? So that also we'll discuss. From an engineer's point of view, from a designer's point of view, from power point of view, and so on. So okay. So shall we continue? So before going into these kind of complex problems, let us have a simple problem at hand. Let us start with the numerical. Let us start with a simple numerical with some values rather than a generalized values. This is the same problem actually, a rectangular pulse only. Only thing is we are taking 3 samples just to have a feel of it. Okay, just to have a feel of it. So what is this question here? So can you listen to me, all of you? So what is the question here? Somebody message. Somebody just message. Yeah. So here is a question. So what is this? Find DFT of a sequence. Find DFT of a sequence. What is the sequence, by the way? X of n is equal to 1 from 0 to 2, 0 otherwise. So see the question here. There are 2 things that author is asking. Okay. Author wants to find a 4-point DFT, and also he wants us to find the 8-point DFT just to arrive at certain inference. Author here wants us to understand the importance of n. Okay, and it starts with some simple numerical. So when you try and do this, probably will understand. Okay, so I hope at least few of you have a pen and a paper maybe, so that you can try these things. Okay. So we have to find the DFT of the sequence. So see here, x of n is actually 1, 1, 1. That means for 0, 1 and 2, it is 1, 1, 1. What will be the value for 3? See, here author is asking us a 4-point DFT. Okay, that means for my x of n also I need to take 0 to 3. Okay, for x of n also I need to take 3 samples or 4 samples. Only 3 exist. So what about the remaining 1 sample? We will assume that 4th sample as 0. Okay, so we will call it as 0 padding. We have taken 1 additional sample as 0. Okay, that is called as 0 padding. So similarly, when author asks us to find an 8-point DFT, since we have only 1, 2, 3 samples, we shall choose remaining 5 samples as zeros. So the concept is called as 0 padding. Okay, so the concept is called as 0 padding. Now suppose my x of n was, say, instead of this 2, say I had, instead of this 2, say I had this value going from 0 to 6. Say I had x of n value going from 0 to 6, then what I would have done? Okay, if at all I had values on 0, 1, 2, 3, 4, 5, 6. Okay, say I had value from 0 to 6, 7 samples, say, and if author asked me to find a 4-point DFT, and say if author asked me to find a 4-point DFT, what I would have done? If author asked me 4 point, then I would have taken value only from 0 to 3. Okay, the value at 4, 5 and 6, I would have simply removed them. Okay, got this particular thing. So you can see. So there might be some very vital information in the samples from 4, 5, 6. Okay, but since I am taking a less quantity of n, I tend to lose this particular information. That is why usually it is logical to take the number of DFT points n always greater than the actual length of the signal x of n, unless it is a very long duration sequence. Okay, unless it's a very long duration sequence. Okay, will you now try, by the way, to find the DFT? Shall we? We'll try this with n is equal to 4. Okay, we'll try this with n is equal to 4. What did I say? At n equal to 0, 1, n equal to 1, n equal to 2, 1, n equal to 3. Let us have a 0 here. It's not mentioned. Let's have a 0. Yeah, 0 otherwise. Okay. Okay. So will you try? I have this some bit here in next slide. Okay. There I have. Okay. So here is the solution. Here is the solution. So how do we do this? By the way, how do we do this? What is the formula? The formula for DFT is x of n is equal to summation x of n from 0 to n minus 1. So when author says n is equal to 4, I shall have the summation from 0 to 3. Okay, my k also goes from 0 to n minus 1, which is from 0 to 3. That means I intend to take 4 samples in the frequency domain. It means I intend to take 4 samples in the frequency domain. So I have to take 4 samples in the time domain also for the analysis. Okay. If at all I have to take 20 samples in the frequency domain, I also need to take 20 samples in the time domain also. Okay. Got it? Got it? So the numerical, okay. So for k equal to c, you can see this is a loop within a loop problem. If at all you have to simulate this in your C or in your MATLAB, k also goes from 0 to n minus 1, n also goes from 0 to n minus 1. Okay, so it's a loop within a loop problem. Okay, so let us start. So how many values we need to evaluate? We need to evaluate for x equal to 0, x equal to 1, x equal to 2, and x equal to 3. Okay, so for every x equal to 0, we still need to do the summation from 0 to 3. For x equal to 1 also we need to do the summation from 0 to 3, and so on. Okay. So shall we? So shall we? So here, first one. So does this expression make any sense? X of n e to the power minus j 2 pi by n. What was the value of n? N is nothing but 4. K into n. Okay, there is a k here and a n here. Okay. So for k equal to 0, in place of n, n is anyway n only, but when n gets multiplied by k, it's going to be a 0. 2 pi by 4. Anyway, e to the power 0 is 1. So that means we are left with x of 0 plus x of 1 plus x of 2 plus x of 3. That's a 3. Okay. For x of 1 now. For x of 1 now. So does this expression make any sense? X of 1. So in the place for k, here, in place of k, we need to insert a 1. Fine. In place of n anyway. Okay. Okay. Then we substitute x of 0, x of 1, x of 2, x of 3. So what is x of 0? See here, e to the power 0 anyway. So it is nothing but x of 0 only. X of 1. So can you tell me what is this value? So 2 pi by 4 is nothing but pi by 2. So this value is e to the power minus j pi by 2. Okay. So can somebody tell me what is e to the power minus j pi by 2? I have requested you to have a pen and a paper with you and a calculator. Anyway. Okay. So can you tell me what is this number? Can you tell me what is e to the power minus j pi by 2? How to expand this? E to the power j theta is cos theta plus j sin theta. E to the power minus j theta is cos theta minus j sin theta. So what is this thing here? This is cos pi by 2. This is cos pi by 2 minus j sin pi by 2. What is cos pi by 2? Somebody, what is cos pi by 2? Cos 90. Somebody. Somebody, cos pi by 2. What is cos pi by 2? What is sin pi by 2? Yeah, yeah, thank you. Somebody. Okay, okay. Cos pi by 2 is 0. Sin pi by 2 is 1. There is a j. So this particular term happens to be, yeah, thank you. Yes. Yeah. So this particular term is minus j. So this particular term is minus j because x of 1 is 1. Okay. So similarly, for this particular term, what is this? Cos pi. What is cos pi? Cos pi. Oh, what is cos pi? Hmm? What will be this term here? X of 2 anyway is 1. What about this term? So this term turned out to be minus j. Okay. This term turned out to be minus j. Cos pi minus j sin pi. What is that? Minus 1. Yes, yes, yes. So this term is minus 1. 1 into minus 1. The third term would have been third term here, x of 3 into so and so. Third term, anyway, x of 3 is 0. So this term is 0. So there we have it. Hmm? Minus j is x of 1. Okay, x of 0 is 3 in the frequency domain. X of 1 is minus j. So minus j means what? Minus j. What is the magnitude of minus j? What will be the magnitude of minus j? Hmm? What is magnitude of minus j? 1 it seems. How do you find the magnitude, by the way? Minus j, how does a minus j look like? So here, right, this is minus j, right? This is the j axis, minus j. So what is the length of this thing? Minus j, magnitude is 1. Okay, what is the phase angle of minus j? What is the phase angle of minus j? Phase angle of minus j is this. See here, it's pointed downwards, right? I start from the origin. So this is minus 90 degrees. So minus pi by 2 is phase angle of minus j. Now, please, somebody tell me on the same grounds, calculate x of 2. Will you please do that? Will you go ahead and calculate x of 2? What will be the expression for x of 2? What will be the expression for x of 2? Now, go ahead, calculate x of 2. What is minus 1 thing? X of 2. What is x of 2? Sorry. See, you will always get confused. Capital X here is the frequency domain. Small x here is the time domain. Now I have found out x of 0, x of 1. Now please go ahead and try to find x of 2 there. Will you please do that? What will be the expression for x of 2? X of n from 0 to 3, e to the power minus j, 2 pi by 4 into, in place of 1, there will be a 2. Okay, will you go ahead and find it? Will you go ahead and find it? I will give you time of how much? 2 minutes maybe. Go ahead on your paper, find x of 2. Okay. So what will be the catch? In place of every one here, there will be a, in place of every one here, there will be a 2. Okay. Will you please give it a try and tell me what is the value? Give it a try and please tell me what is the value. X of 2. Till then, let me uh, okay. Now what are you seeing on your screen, by the way? Now what are you seeing on your screen? I just closed that thing. Okay. Yeah, please try x of 2. Please try x of 2. Can you listen to me? Somebody please message, can you listen to me?
Yes, sir.
Okay. Please try x of 2 now. Please try x of 2, so that in the meantime I will put that what the answer, image of the answer here on my screen. I could not copy that properly. Yes, somebody, x of 2. Yes, could somebody find x of 2? Could somebody find x of 2? Hmm? Anybody? What is the catch there? Anything tricky in that finding x of 2? Anything tricky there in finding x of 2? Now somebody entered. Hmm. Could you? Yeah. Okay. Sorry for that. Yes. So did you find x of 2 there? So we are back. Did you find somebody x of 2? Anybody? No? X of 3? Somebody x of 3? Not interested in participating? Hmm? Say there is x of 3. Hmm? There is. Are you still there? By the way, everybody say hi. Type a hi there in our this thing. Okay. Huh? Huh. Okay. This everybody is responding. Yes, Namrata. Anything? Hmm. So x of 2. What happened by the way? X of 2. What number did you get? So did anybody get this particular thing? Did anybody get this a 0? Did anybody get a 0? Hmm? No? Did you not get a 0 there? X of 3 by the way. What is x of 3? Hmm? So here is the expression for x of 3. Okay. J. X of 3 is j. Yeah. So you got it or it's from here. Okay, fine. Hmm? Whichever the way you choose. Okay. There. That is x of 3. Okay. So that is how. So the trick to digital signal processing is by making friends with that j. Okay. So if at all you're comfortable with the complex operations, and it's going to be much easier. Okay. So there for x equal to so x of 0 is 0, x of 1 is minus j, x of 2 was expected to be 0. I don't know how many of you got that. X of 3 is j. There you have it. Okay, this one will come to this. We'll come to this when we discuss n is equal to 8. Okay, we'll come to this and when n is equal to 8. Okay, so here we have the value. So complex values are difficult to draw, but what you can do is we can always plot the magnitude and phase separately. Okay, the trick is to plot the magnitude and phase separately. Okay, so here you can see what is the magnitude of 3. Magnitude of 3 is 3. What is the phase angle of 3? 0. What is the magnitude of minus j? 1. What is the phase angle of minus j? Minus pi by 2. How do we find the phase angle? Tan inverse imaginary part by real part. Okay, tan inverse of imaginary part by real part, isn't it? So what is the phase angle of a plus jb? Somebody please help me. What is the magnitude of a plus jb? Somebody, what is the magnitude of a plus jb and what is the phase angle of a plus jb? What is it? Will somebody help me out? What is the magnitude of A plus JB? Should I? You can, yeah, unmute themselves. I have allowed you to unmute. You can unmute and you can tell the answer. Typing is difficult. What is the magnitude of A plus JB? What is the phase angle of A plus JB? Hmm? Okay, nobody is interested. Okay, so now what the task I'm going to give you is, you calculate the DFT for n is equal to 8 on your notebook before we come to next class. Be curious, it might be there in somewhere in the textbook also. I don't mind you copy or something, but please, your small assignment, homework, small homework for today